can start.
I can start. So we are talking about the biological aspects of microbial influenced corrosion. So what is it? It's a special phenomenon on structural steels, and we had a possibility to observe what's going on under water by a dry setting installation in a cooperation project with a private company. So accelerated water corrosion seems to be the research topic of engineers, and there is very little input of biologists, mostly of microbiologists, on microbial influenced corrosion. But there is more about fouling. There is underwater a living community on the substrate of macro and microorganisms, and this is much more than bacteria alone. We have to do in fouling with big organisms like oysters, mussels, barnacles, sponges, etc., etc. Looking at the transect of the water column in contact with a substrate like a rock, we have a biofilm with a lot of biological metabolic activity, summarized as oxygen consumption and the production of acid, metabolic end products. It's so that fouling is microfouling of bacteria, unicellular algae, protists, fungi, etc. But on the other hand, we have also macrofouling of mussels, oysters, etc., as I said. Now, if we switch a substrate from rock to iron, we have a very strange phenomenon, because biologists don't like it and don't look at it anymore, and engineers are not interested in biofouling. However, looking in some more detail to that no man's land, we see that a corrosion film has mostly three main layers: an orange outer layer, a black intermediate layer, and a greenish innermost layer. Now, in the biomat, who is quite thick, with a lot of activity of organisms that result in heavy oxygen consumption, in a way that near the substrate the medium becomes completely anoxic, and that's an ideal environment for sulfate reducing bacteria. Heavy fouling flakes off by mechanical removal, and as a result there is a patchy distribution of clusters who are growing and disappearing in a dynamic succession, resulting in fluctuating corrosion cells. Now, in that anaerobic environment of lithotrophic corrosive bacteria, sulfate-reducing bacteria produce iron sulfide, and that black crust is a layer that has electrically conductive properties. When growing, iron sulfide thickens, and underneath you can have a growth in layers, and we see by transect analysis that in a period of 2 years, up to 2 centimeters of iron of a sheet pile can be consumed. Moreover, lithotrophic corrosive bacteria induce not only chemical MIC but also electrical MIC. This means that there is direct electron uptake from the iron sheet pile named electrotrophy. These cells, the bacterial cells, are connected to the substrate with special nanowires for electron flow. So, in summary, metallic iron is a recent compact electron donor for the bio community. It's giving a lot of energy. It's a hidden process under black crusts or under so-called tubercles. And we have to say that steel in an aquatic environment is a misapplication when your surface is not protected by a coating. In conclusion, use effective coatings so that you have an environmental barrier to the substrate that prevents corrosion. Second, you need life cycle management, so spend more money initially and less on maintenance cost in the future. And cathodic protection can be inefficient, and moreover, zinc anodes can produce heavy metal pollution to the environment. Thank you for your attention.
Thank you.